Yo, what's happening, Engr?
Yo, what's up, Josh? How's it going,
Hello? How you doing?
man? Just got breakfast and got ready to continue with the lecture. Have you watched the videos?
I actually haven't. I was just popping in here to see if
I
Cost was going to make any announcements at the beginning. I plan on going back and watching all the lectures after school's over.
see. Pretty cool, man.
Yeah,
Yeah, I don't know.
yeah. I was kind of bummed. I was hoping to attend all the extra ones, but last week I got like hit with a bunch of deadlines I had to complete, and I wasn't able to make any of them, which is kind of a bummer. But yeah, I'll go
Uh,
back and watch them.
I feel you. It's a time of a semester where you get bombarded with a lot of assignments and
Hmm.
exams coming, trying to finish up
Yeah,
everything, making sure that you have all done.
definitely.
Dude, I had like this three. It was like a 4 pages essay. I got like 3 weeks to work on it, and I started and finished it yesterday. So you
Nice.
can tell.
Hey guys, what's up?
Hey, Carlos.
How you
You
doing,
guys doing all
Carlos?
right?
Pretty good. Pretty good.
Yeah.
So I also wanted to say something to you, Edgar, before we get started here.
Okay.
It can also apply to you too, Josh, if you're interested. Josh made a really interesting remark. He says, and so he's going to be, not this Josh, the other Josh, Brooke, he's going to be holding on to the circuits equipment throughout the summer. And I have agreed to post 4 AC labs. And so he's going to go through them. I don't know if that's of any interest to you, but that's something that, for you to think about if you want to do that. I'm going to send an announcement if any of the EEs or anybody wants to hold on to the equipment to do something like that. I'd be totally down with it.
That would be awesome, actually.
Yeah, because I have 4 AC labs that we didn't do. And one of them is filters, which I think is a really good one.
Mm-hmm.
But anyways, that's where we're at. So let's go pick up where we were last time here. So one of the things that we said here, we should just come kind of go back and review briefly, because now I'm going to try to get into sort of like the phasor algebra and just try to get a sense of what we're talking about. And so I think one of the things that we said here is we said something like this here. Let me make sure I get my window set up here, because now it's just calculation after calculation after calculation after calculation. And what we said here is that when we start with the ordinary time domain circuits, and we want to transform into the complex plane, what we do here is that we take each of our components, R, L, and C, and we then convert them. We convert them into vectors on the complex plane. Once we do that, we now have a phasor circuit. And because the units of L and C are now in units of ohms, they behave as linear elements. So that means we then can go back and use all of the stuff that we used in the beginning. So that means we could use voltage divider, current divider, rules for calculating, currents and voltages across, capacitors and inductors, which is, as I said before, that's really strange. You can take an inductor and you can take a capacitor and treat it as a linear element, no differential equations. So then we then say that there's this AC equivalent resistance, which is the impedance, and the impedance has a magnitude and it has a direction or a phase. And so then we start to look at the phasor diagrams. What are the phasors? So we could see where XL can be greater than XC, or XC can be greater than XL. And so the vector of the impedance then tells us how this system actually behaves. And so that becomes really important. But what you're going to see here is that now that that's the case, now we could go in and we can start applying this, linear thinking with phasors here. So once we have that, now we can apply all those rules. And that's where we were last time. We went through really just 2 simple examples. Now I want to get into more complicated examples. And what you'll see here is that in this case here, what we're going to be doing is that we're going to really be starting to look at this thing a little bit more, a little bit more clear. So let's do that. So what we have here is that we have this circuit here, and it looks fairly complicated. And so what I want to do this time is that I really want to start applying sort of like the thinking that we want to do to actually solve this circuit. So once again, what are we doing here? We treat inductors, capacitors as linear elements. So if we look at this thing, just kind of check this out. So in the time domain, this is a 4th order differential equation, right? That's pretty scary when you think about that. That's pretty scary just to think about that. And the reason why it's a 4th order is that note that I can't reduce these capacitors and inductors. So that's one thing here. Also, note the source. It has a phase. So we can't ignore the source now. So let's go do this here. So what we're seeing here, so now what we want to do here is that we want to convert this into a phasor circuit. And then in the end, what we want to do here is that we want to look at, well, what's really happening when we look at these things. So the first thing that I'm going to do here is that we could see here that omega is 4 rads per second. So let's go look at these things very carefully. So the first thing that I'm going to look at is I'm going to look at the source. The source here is 10. Let me be careful here. It should be Vs of t is 10 cosine 4t plus 60 degrees. So in phasor form, this is going to be 10 volts with 60 degrees. That is different. Now, we should be careful here. And the reason why we should be careful here, because one of the things that we're going to have to do here is that we may go in and put this in rectangular coordinates too. Now, is it worth putting it into rectangular coordinates? Well, I mean, right, we could write this also as 10 cosine of 60 plus J10, sine of 60. And if I remember correctly, this should then be 5 plus j, I think it's the square root of 3 over 2 times 10, which would be what? I think it's 8 point, right? I think it's 8.66 volts. Sometimes it's more convenient to put it into rectangular, and sometimes it's better to put it into polar. Depends on how you're solving the problem. I prefer to keep things in terms of polar, which I'll leave it like that for right now. So then I have 2 caps, 2 inductors. So let's go do that. So if I look at the inductors, I have a 10, I'm sorry, the capacitors, I have a 10 farad capacitor. So then this tells me here that this guy's going to be omega C1. Maybe I should have done that here. How about if I do this a little bit different to be a little bit more clear? Let's call C1 the first capacitor. So therefore, X C1 is then going to be omega C1. So if I put that in, it's got to be 4. And then I'm going to get 10 times 10 to the negative 3. So obviously that's 10 to the 2. So that's got to be 100 divided by 4. So it's got to be 25 ohms. This immediately implies that C2, which is twice that, which is half that value, that means since C is in the denominator, it should be 50 ohms. So then this immediately tells me that XC2 should be then 50 ohms. Let's do the same thing with the inductor, since they're kind of set up that way. So the first inductor is 2.5. So let's go look at the first inductor, which is 2.5 Henry. So therefore XL1 should be omega like this here. So this should be 4 times 2.5. So then this is 10. So if I have a 5, which is twice of this, that should mean then that this guy should be something like this. Should be 4 times, twice as big. So now I got all things here. So what I'm going to do here is that I'm going to try to see if I could try to understand what's going on. So what I'm going to do is that I'm going to redraw this as blocks. Okay. So I'm going to redraw the circuit. Into blocks. In other words, what I really have is that I have a source. So if I look at my phasor circuit, this is going to be 10, 60. Then I'm going to look at blocks like this. So if I look at these blocks here, what I'm really seeing here is that I'm going to call this Z1 and I'm going to call that Z2. So the thing that we're actually solving for in this case here is that I forgot to mention this. We're talking about getting the voltage across this thing. So ultimately, to determine the voltage of L2, which is the voltage across the 5 Henry as a function of time, that really means that we really need to get, we need the voltage across Z2, since Z2 contains that. And once we get the voltage Z2, you could see here that then Z2 is also the voltage of the inductor, since those two elements are in parallel. So that means here that the voltage across C2 is also the voltage across, let me be careful, across the XL2. So let's go do that. So in order for us to do that, what we'll have to do here is that we're going to have to go in and actually calculate that voltage using voltage divider rule. So now, so let's use VDR to get the voltage across Z2. So we can see here that the voltage across Z2 is then going to be, according to the voltage divider rule, it's the impedance of block 2 divided by the sum of the impedances times the source. So I really got to figure out what Z1 is and Z2. So here we go. Let's start with Z1. So if I look at the first block, this is the same as the following thing. So it's going to be a resistor, and then I have a cap, and then I have an inductor. So according to our values up here, you could see that the first one is L1, so it should be J10, and the inductor should be minus J25. So if I come up over here, this should be J10 ohms minus J25 ohms, and then the resistor in this case was 20. So you can see here that these two are in parallel. So what this means here is that it has to be J10 parallel to 20 minus J25. So let's go do that. So if they're in parallel, I could just do the standard types of tricks here. So it's got to be what? I multiply both reactances or impedances divided by the sum of them. So it's going to be like this. So it's going to be J10 times 20 minus J25 divided by J10 plus 20 minus J25. So if I look at this thing, again, you're going to see that the top here, if I multiply J times minus J, that's positive. So I should get 10 times 25, so give me 250. Then I got to multiply 10 times 20, which is 200. Yeah, so that's got to be plus 200J. And then if I look at the denominator, that's 20 minus J15. So how do you go from here? Well, I would probably break this into polar form. Okay, so if I was to do this into polar form, it gets real ugly real fast here. The numbers are quite big, so what I would probably do here is that I would immediately divide everything by 10. So if I divide everything by 10 here, this will be 25 plus J20, and this would be 2 minus J1.5. So then if I start to actually do this here, remember this has to be converted. So if it has to be converted, then, right, it's got to be 25 squared plus 20 squared. And if I get that magnitude, let me see, let me bring this over here. So then this has to be 25 squared, 20 squared square root. And then I have to take the tan inverse of 20 over 25. And if I look at just the first one here, it's going to be 32 point, let's say 02. And then the angle here that we're going to get here has to be, is that 20 divided by 25? and I get an, oh damn, of course. This has to be 20 divided by 25. And I'm going to get 38.66 degrees. And you can see how this starts to get really ugly very, very, very fast here when you start to do this here. And then if I do the same thing with this guy, I'm then going to get, so this guy's going to be 2 squared plus 1.5 squared. And then, of course, this will be the tan inverse of 1.5 divided by 2 with the minus sign. Then I'm going to get 2.5. And then my angle in this case has to be, what is that? Minus 1.5 divided by 2. I'm going to get minus 36.87 degrees. So now if I repeat this process, then I'm going to get 32 divided by 2.5. So this is going to be 12.81 ohms. And then the phase angle in this case here, you could just see here that I just have to add these two. And this should give you a phase angle of 75.5 degrees. So I don't know if you noticed this last step here. So just to be really clear, here's what I want to do here is I want to elaborate on this step right here. What this really reads is 32.02 e to the j 38.66 degrees divided by 2.5 e to the minus j 36.87. So if I look at this, this is really 32.02 divided by 2.5. And then of course the powers of exponentials is just, when I bring up the denominator one, it just gives me 38.66 plus 36.87. And that's how I got to 75. So right now, when I look at Z1, this is what I'm getting. So that's the reactance right there. So now that I have that, I'm not going to do this for the second one, but we can sort of like write this out here. And if I do this, what am I going to get? So for the second one, I now have this impedance, and this guy reads like this. I have an inductor all by itself again, so it'll be J20. And then I have a cap and a resistor. This guy's 40, and this guy's minus J50. Again, this is J20, and this guy's going to be 40 minus J50. So if I look at this guy here, what am I going to see here? What I'm going to see here is that this is going to be J20 times 40 minus J50 divided by the sum of J20 plus 40 minus J50. And you could see that there's an issue of 10 now. You could see that I can divide by 10 on the numerator and the denominator. So this, let me spread this out here. So I'm going to factor out a 10 in the numerator and the denominator. So if I take a 10 out, I really have J2. So then this should be 2 times 50, which should be 100, plus, if it's 2, it's got to be J80. And then in the denominator, I have minus 50 plus 20, So that's going to give me minus 3j, and then this guy should be 4. And I think this is a little bit cleaner here. So then we would actually do this like this here. Or another thing that we could do is that this is what I typically do. You can use your calculator. So if you go, I think in your calculator, what you have to do here, if you have the right calculator, you have to go into the mode, and then you got to go into the complex mode, and then you go into, you could either do it in the rectangular or you could do it in the polar form. But if it's in the rectangular form, then you just multiply, you divide these two quantities. But, here's what you end up getting here. I'm a little suspicious of the answer that I have. I think we should check this real quick. So this should be 100 squared plus 80 squared square root, and this will be the tan inverse of 80 divided by 100. And this guy's going to be 4 squared plus 9 squared. You can see that's 5, right? So then I got to get the tangent inverse of minus 3/4. So if I look at this number here, just because I'm doubting what I'm actually seeing here, I'm going to get this. I'm going to get 100 squared plus 80 squared. So this gives me 128.1. And then this guy should be 5. So that divided by 5 gives me 25.61. So I'm seeing here that this guy's going to be 25.61. Here's where I'm worried about, because my calculation shows that it's 75.5. I don't know if I believe that. So let me check that number just to make sure. So then the angle should be 8 divided by 10. So then this angle should be 38.66. And this angle should be what? Negative 0.75. And this is minus 36. Wow. Why are these angles the same? The angles are exactly the same, which I'm a little bit surprised. We'll look at this thing here in a minute of what this actually means here. So now, I now have my circuit. So my circuit looks like this. So I have a voltage source. And then I have impedances. And I got this guy, and I got that guy. So then Z2 is 25.61, and this is 75.5. And then this guy over here is 12.81. And again, this is 75.5 degrees. So now, if this is Z1 and this is Z2, then VDR tells me what? Tells me that the voltage across the second impedance is then going to be Z1, Z2 divided into Z2 times my source. So if I look at this thing, what am I seeing here? That this guy is then going to look something like this. It's going to be 25.81, 75.5, plus 25.61 times 75.5. And then this guy's going to be 25.61 times the phase of 75.5. And then this should give me 10 volts with 60 degrees. Now, I don't know if you realize this, but look at the numbers here. So let's put this into polar form. It's already in polar form, but let's write it out in terms of phasor vectors. What you're seeing here is that this is the same as 12.81 e to the j 75.5 plus 25.61 e to the j 75.5 divided into 25.61 e to the j 75.5 times 10 volts at 60 degrees. So right away, you can see here is that the phase immediately cancels out. And so I'm left with a number here, and that you can see that the phase ends up being 60 degrees. So if I get 25 divided by these guys here, what am I seeing here? 25 divided by 37 times 10. So I got to have a number less than 10. So this is 25 divided by 37. That looks like it's about 60%. 60% times 10. So let's go calculate that number. So if you punch this into your calculator, this is what I end up getting. Oh, damn it. You get that this guy is 6.67 with a phase of 60 degrees volts, and this is V2. So what the hell does all of this mean? Okay, what does this mean here? Well, it means it has to look something like this. So let's go look at, let's draw the phasor diagram for this. So if I look at the phasor diagram, here's what I'm seeing here. If I look at the current, let's look at the current. If the current comes in here, it starts off with a phase of 60 degrees from the source, but then as it goes through this source, it gives it a phase of 75. And then it comes through here, and you can see that the current is still gonna maintain a phase of 75. So if I look at this thing, what do these vectors actually mean? Well, it means something like this here. If I look at the total impedance of the circuit, is this. Has to be this. And if that's the case here, this has to be 12.81 plus 25.61 times this phase of 75.5 degrees. And if we add those two up, that should be, what is that? 25.61 plus 12.81. That's got to be what, 37? Should be about 38.4 ohms at 75.5 here. So if I'm looking at this thing, what I'm seeing here is that I'm really seeing, so if I look at the impedance, what you're seeing here is that I have a phasor. And you can see here that because this guy is positive, that means it has to be more inductive. In fact, it's acting almost like an inductor. And so if I break this thing up here, if I look at the total impedance of this thing here, you could see that I get 38.4. So let's break this down just so you could see what I'm talking about. So if I break this down, what I'm really writing here is that I'm writing this here. I'm going to get 38.4 cosine of 75.5 plus j 38.4 sine of 75.5. And so if I compute this, I'm really getting this guy right here. The first one's going to give me 9.65, no, 2, plus j. This is going to give me 38.4 times sine of this guy. And this guy's going to give me 37.18 ohms. So when you're looking at this thing, remember, when I look at the phasor diagram of this guy, you could see that the L component, right? Let's make this essentially one square. So if you could see that this XL component is huge compared, you know what, I'm going to move that out of the way, compared to the real part. So if you look at the real part, that real part is real, you know, it's about 1/10 of the value. And then this guy is a monster. So you're seeing here that this guy, the impedance is very inductive. And that's because this angle is 75. So in other words here, the inductors dominate each impedances in Z1 and Z2. So you could see here that this phase angle is absolutely monstrous. It's a huge phase angle. So immediately what this tells us here is that when we start to look at the circuit here, we expect then that the voltage leads the current. So in other words, if I'm looking at a diagram, and if this is my, let's say that this is my voltage here. So if I'm looking at the voltage, either voltage 1 or 2, we would expect here that when I look at the current, let's say this is the current right here, there's going to be a phase difference. I didn't draw that right, did I? It's almost like this guy is starting out of phase by 90 degrees, right? So I guess I did have that, didn't I? And so what I'm saying here is that when you go and you look at this phase from here to here, the phase difference between here and here is 75 degrees. And that's a big, 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 big difference here. And that's essentially what we're talking about when we're dealing with the phase vector. Okay. Let's go look at, oh, wait, we're not even done with the problem yet. Because I think what the question asked, let me see if I'm right. Let me go back up here. It's asking for the voltage VL of t, so it wants a time domain. So here we go. So then check this out. So if I want to, so now let's transform back into the time domain. And so what we do here is that then we take the real part of the voltage in the complex plane, which then means that I take the real part of what? Of a 6.67, and this guy should be 60 degrees. So then this should be 6.67 volts cosine of 4t plus a phase of 60 degrees. And that is the voltage of the inductor. Right? That is the voltage of the inductor, which is pretty awesome. Right? That's a very, very, very nice solution here. Now, one of the things that we should really kind of think about, why do we even care about the phase difference between the inductor and the voltage here? Well, this example, believe it or not, is very, very, very similar to the ring launcher. Okay, so as an example of why this is important, think about what's known as a ring launcher. Now, if you know what a ring launcher is, it involves Faraday's law. And so what you typically do here is that you have an AC source, and the way right, so you could imagine that you have this source here. And what this is here is that this guy is, of course, connected to the AC. So this is an AC outlet connection. And this guy right here is a pulse source, a AC pulse source. And what you typically do here is that you take a rod, and then what you go in and you do here is that you go in there and you do windings now. So what you're going to do here is that you're going to put a whole bunch of windings. So what you have here is that this guy here is, of course, a coil. In other words, it's an inductor. And so what you do here is that what's common is that you come in and you put a ring in here. And the whole goal of the ring here is that, according to Faraday's law, so as soon as you turn in the pulse, what you're going to find here is that Faraday's law implies that the changing magnetic flux induces a voltage on the ring, and from this you produce an induced current. And that induced current, then what you find that ends up happening here is that you get the following thing. Because they're opposing each other, what you're going to find here is that if you look at the ring here, what it's going to do here is that it's actually going to produce a magnetic field in that direction. And this is the induced field. Because what's happening to the coil? Well, when you look at the coil here, the coil's magnetic field is then producing a field in this direction. So what you're finding here is that you get two opposing fields, right? You produce an, and then you get, so you produce an induced current, you produce two B fields in opposite direction. So one gets a jump. In other words, the ring is launched, right? That's what they tell you. Not so fast. This is an incomplete explanation. And the reason why it's incomplete is note that this source is AC. So that means for 1/60th of a second, we have opposing fields, and the next 1/60th of a second, we have attracting fields. This implies the ring should not be launched. It should not be launched. But the problem is, it is launched. However, the ring is launched in real life. Why? And it's called Eli, which means here that the induced voltage leads the current. And so what happens here is that when the coil, okay, when the coil induces a field in the ring, induces a field in the ring, it has a jump start on the AC source. Why? Because Eli, the voltage of the inductor, leads the current. So what happens then, it has a jump start, so that means it's ahead of the changing AC source and leaves before the AC can bring it back down. In other words, it's important to have the difference between the phase of the induced voltage leading the current, which I think is super cool. That's a very, a lot of times people say like, oh, why would you want to do this? Why is this even important that the current leads or the voltage leads either the current or the voltage, depending on how you're looking at it. But that's a prime example of what we're talking about right there. Okay, let's move on. I don't know if you've ever seen that before, but I think it's a really, really cool example of an application of this, of why AC is important. And I think my next example is a is a capacitor one. And the capacitor one becomes really important too for other reasons, which I'll go in and we'll look at why is a capacitor so important here. Okay, let's go look at this thing here now. So if these guys are linear, then one of the things that we can do here is that we could go in and we can just start looking at, you know, sort of like, how do I apply node analysis? So let's go look at this thing here. So what you're seeing is that I want to use this to determine, I want to determine the voltage across the cap, as you can see. So let's go pick our nodes. Of course, this is ground. And then I could see that I have two nodes. There's one node right here. And then there's this node right here. Oops, bad. And then there's this node right here. So we could call this any way we want here. I definitely want to call this node VC here. And it looks like it might be useful to call this node V10, since that's what the node is right there. So what I want to do then is that I want to go in and I want to I actually want to look at this thing here. And I think I want to do all the hand calculations by hand, just so that we could get a better sense of how do I handle all of these calculations. Okay, so what we're seeing here is that we have two nodes, two unknowns, which will be V10 and VC. Okay, so let's look at the 10 node. So if I look at I'm going to look at node V10. So I could see here, if I just use the standard techniques here, so it's got to be the inverses. So it's got to be 10 plus J51 times V10 minus the mutual, which is this J5 here. So it's got to be times VC. And then I got to look at all of the sources. I could see what's flowing into the circuit here is then going to be this guy. But since that's 0, I'm going to just assume that this is just 2. Now, since I'm going to try to do a hand calculation, I'm going to convert this current source. So if I convert the source here, this should be the square root of 2, and this should be cosine of 45 plus j sine of 45. And we know that 45 is the square root of, right? It's the square root of 2 over 2, which is 1 over the square root of 2. So then this should be equal to 1 plus j. So that's what's going to be my current source here. So now I'm going to focus on node VC. And if I look at this here, you can see that I have 2 in connection here. So I'm going to get minus J4 plus J5. That's got to be VC. Any mutuals, I got 1, which will be J5 again. This will be V10. And then my source here, which is coming into the node, should be 1 plus J. So now what I'm going to do here is that I'm going to try to clean this up a little bit. So if I look at the first equation, I'm going to try to simplify these equations. So I'm going to call this equation 1 and this equation 2. So I'm going to multiply equation 1 by 10. And if I look at the second equation, because of the 4 and the 5, I'm going to multiply that by 20. So let's see what happens if I multiply the first one by 10. So if I do that, then I get 10, I'm going to get 1 plus, right? This is going to be, I'm going to get 2 divided by j minus j to 2. And then this guy's going to be 20. But now I'm going to be clever here with my sign notation here. And the way I'm going to be clever with my sign notation is that if I have j in the denominator, I could bring it into the numerator. And if I bring it into the numerator, you know, another thing that we could have done, we just could have multiplied everything by 10j. Maybe we should, well, actually, I'm just going to do this. So 1 over j is the same as minus j. Minus j in the denominator is the same as j. So if I do that, this is really 1 minus j to the 2. And then this guy's going to be plus j2, 20. So here's my first equation right here. Right, that's my first equation. And if I look at the second equation, I'm going to do this while moving a little bit faster here. So if I multiply by 20, of course, I'm going to get 5, but then minus j becomes j. So this is going to be 5j, and this will be minus 4j times VC. And then this guy's going to give me positive J4 V10. And then again, this will give me 20 plus 20j. So if I clean this up a little bit, you'll see that what I'm going to get here is that I'm going to get JVC plus J4 V10 equals 20, 1 plus j. So now I'm going to use Cramer's rule. Okay, I'm going to solve this using Cramer's rule. So I have a matrix, right? So here's my VT, and then let's go VC. Then of course these are going to be my constants. So this is going to be 1 minus j, 2, and then the other one's going to be j4. VC is going to be j2. This is going to be j, V10, VC. Then my constants are going to be 20, 20, 1 plus j. So then this tells me here that VC then, I'm going to replace my constants with VC. So then this is going to be 1 minus j2, j4. Then here's my constants. And then it's got to be the determinant of the cofactors. And it looks like this. So now it's just the algebra. So if I look at this algebra, I think I'm going to move this down. So my algebra looks something like this here. So it's got to be that times that. So I'm going to get 20, and I got 1 minus j2, 1 plus j, minus j80. And then if I look at this guy here, I'm going to take that j inside. So I'm going to get, look at that, j times minus j is 1. So I'm going to get 2 plus j minus, so then I'm going to get j is minus, and then I get a minus, so that's 1. So then I'm going to get plus 8. So if I clean this up here, what am I getting here? Well, you could see that I got 1 times 1, right? If I look at 1 times 1, I got 20. So I'm going to get 20, and then I got to get the j terms here. So then the j terms is going to be plus 20 times the following thing. So I got minus j times 1. So I get j2, and then I get j times 1 plus j, and then I got to multiply 1 times 1, which will give me 1, and then I get this minus j80 divided into 10 plus j. So then if I do all the cleanup here, note that I get 20 plus 20 is going to give me 40. Now let's look at the j values. So I'm going to get minus j2 plus 1. So that's minus j. So I'm going to get minus j81. Oh, no. That's not right. This is going to give me minus j20 minus j80, which in this case is going to be 40 minus j100 divided by 10 plus j. Assuming that I got my algebra right, I think my algebra is right. Oh, no, it's not right. You know what I forgot to do here is check this guy out. I didn't do the j's. So that should be plus 2. And I said plus, right? That should be plus, is that 1 plus 3? Here, let me make sure I got my numbers right. I got 1 times 1, that's 1, minus 2 j times j, that's 2, that's 3, that should be 60. This should be 80, not 40. So that's what this thing is right here. So now what do? We got to convert this into polar form. So this means 80 squared plus 100 squared. Then I got to get the tan inverse of minus 100 over 80 divided by 10 plus 1 squared, and then the tan inverse of 1 divided by 10. So that's what we got to get. So then if we go start calculating these guys, what am I seeing here? Well, if I calculate the first one, I have a magnitude of 128.1, and then my phase angle should be minus 100 divided by 80. This guy should give me an angle of minus 51.3. Okay. And then if I do the exact same thing here down below, I'm going to take the square root of 11, which we already know what that is. It's pretty much just a tiny bit over 10. I'm sorry, no, the tiny bit over 3. And then the phase angle on this guy is then going to be 5.71. So if I look at this thing, what do I have? I have 128.1 divided by 3.31. So this will be 38.7 volts. And then my phase angle, you could see here that when I add these guys together, I should have a phase angle of minus 57.01 degrees. and this is the voltage of the capacitor. So if I look at this thing, what does this all mean here?
I think we should check our magnitude again.
I can't hear you.
Can we check our magnitude again? The 3.31?
Say that again?
The 3.31. Where do you get that from?
Is the square root of 10 not about 3?
No, but it's the square root of 101. Because we have to square the 10 and then add it to 1.
Oh, shoot. Yeah, I agree. It's about 33.1. Yeah, thank you.
No. It should be around 10, isn't it?
No. I mean 10. Sorry about that. I don't know why I said that.
That's fine.
I was multiplying by 10. So it should be 10. I even said 10, and of course I didn't actually do that. Yeah, so it should be around 10. I have, right, it's got to be, I mean, I don't know about the sig figs, but the sig figs got to be tiny. Maybe that amount. So then this should be about 12.8 volts. That's what my guess is right there. So that's what this is. So let's say that this is what it is here. Well, what do we know about this? Well, I think what we're seeing here is that in this case, if I was to look at this voltage, let's go look at this guy here. So again, what we should do here is that we should break this up. And of course, the way we're going to break this up here is that the way we're going to... Wait. You know what? Did I forget to... No, I changed my source here. So when I look at this, this should really be 12.8 cosine of 57 minus j of 12.8 of sine of 57. So if you're looking at this thing here, then what I'm going to have here is that I got to have this guy right here. This is going to give me 6.97 volts minus J of 57. And this will be 10.74. So when you're looking at this guy here, what you're seeing here in the complex plane, that's telling me that again, that this voltage must have a component that, let's say it's about this big, right? So this is going to be this, this complex one right here. And then the other one is just going to be about half of that, maybe a tiny bit bigger here. So you're going to see then again that the real part and the imaginary part, I don't really want to put XC because it's not XC here, but this is, maybe I should write it like this here. Maybe I should write this as just VC, and this term I'm going to write as JVC. And again, when you're looking at this voltage, you could see that it's definitely below the axis here. And again, when you look at this phase, we see here that this phase here is 70.01 degrees. So the question is, why is this important? And a couple of things that we should see here is that in this scenario here, what we're seeing here is that we're seeing the so-called ice. So when I look at this thing here, here's what I'm really seeing here. I have two waves. let's say that in this case here, I have a wave that's moving like this. And these waves all have the same phase. And this is the current going through that cap right there. Right? Because when we're looking at the voltage of this cap right here, we're really looking at the voltage across this minus J4 cap right here. And so what that means here is that when I'm looking at the circuit, here's what I'm seeing. I have a current source. I have a resistor. I have an inductor. But this is the guy we're really looking at right here. And so what you're seeing here, I'm sorry, Edgar. For some reason, I did not turn off my phone, my voice thing. And so what you're seeing here is that then I have this current source right here. So what are we actually seeing here? So what you're seeing here is that you're seeing this, that there's a current that's actually flowing right here. And that current, and we're also looking at this voltage right there. And so what we're going to do here is that I agree that we calculated the phase of the capacitor voltage. Okay, the capacitor voltage. And so what this is really telling me here is that when I look at the voltage of the capacitor, the current, right, this tells me here that the current leads the voltage. So when I'm looking at this guy, that means that the current is ahead of the voltage. So when I look at the voltage is going to be, let's say, over here. Let's see if I can draw this. I always have trouble drawing these guys here. Let's see if I can get this right. And so what we're seeing here is that I'm actually going to move this current out of the way. When I look at this current here, and then this here, of course, is the voltage. And what you're seeing here is that there's a difference between these peaks right here. And what's the difference between these peaks? 55.01. Now you may say, like, so what? What does that even mean here? And the one thing that I would say to you is something like this. So what I'll do here is that the way I'll answer you is that I want to think about an example. And we want to look at smart meters. So on your home, PG&E has installed these so-called smart meters. And what's really important here? So when you look at the inductance, I'm sorry, I said inductance. So the natural impedance of your home is more inductive. That's the natural impedance of your home. And you might say, like, why? Well, look at how the wires are set up in your home. You have these large loops, right? If you look at your washers, right? So if you look at the wires in your home, how are they wired, right? You got copper wires that are forming loops all over the place. You know, all of your appliances are more inductive than capacitive because of the motors that run your appliances, right? If you look at your toothbrush, what's your toothbrush? Your toothbrush is nothing but a coil. That's how it's charging up the battery in, you know, in there. So what does a smart meter do? The smart meter, so actually, let me be careful. So the home is more inductive. So if you look at this thing here, if I look at a phase diagram, that means that your home is more like this here. Let me be careful. It's not at 90 degrees because there's some resistance, but what you were seeing here is that you're going to see that the impedance of your home is then going to be more inductive. So it's, you know, it's pointed along that direction. The problem is that high inductive reactance impedes the flow of current, right? So when we looked at this guy, we saw that it does this type of thing, but we want as low as flow as possible. But we want to reduce this impedance of the home. So what they do here is that your smart meter does what? It comes in and it adds an impedance in the opposite direction. And so the goal here is to kill off the imaginary part of this thing. And so what happens then, if you do this, the goal here is to try to make your home as much resistive as possible. So the goal is to kill off the imaginary part of the impedance. And then just only make it then as resistive as possible. And so your smart meter comes in and it purposely adds a phase in the negative direction to literally kill this stuff off here. So I think it should stop right here. But, you know, I don't know. Have you ever heard those examples before?
No, this is the first time actually. Quite
Yeah.
impressive.
So, but hopefully that kind of makes sense here. Yeah, I think it's surprising that the meter is kind of pretty badass the way it works, right? Because it's literally killing that vector that's going up, and it's purposely putting this so that you get it only resistive. So it's only that there's no other impedance in the circuit other than the resistive nature of the wire. Otherwise, you're not getting maximum power into your house. Yeah, okay. I'm gonna stop here and